All right, hello everyone, April the 3rd. All right, I will solve this one first. And for this one, I actually did think about it. Well, actually last night I tried to and I fell asleep. So I thought about it, I think during my rest while I lived today. So I think what I'm gonna try is I'm gonna try binary search. Okay, so what I'm gonna do is because Okay, so because the cost is just the leftmost and the rightmost index, right? And if you remove those and then say the remaining is going to be a subsequence, so we can also remove everything in between. Then the remaining shall still be a subsequence, right? So therefore, we're looking for is we can do like a sliding window kind of thing, right? So we say, I want the distance between the left, because I want this, right? This is the length. I want this length to be as small as possible, right? What's the smallest? So I know, put 1 in there, binary search, right, for the length. And all we need to do is just to check when we set the length to be a certain value, does the remaining fit as a subsequence? So we just need to do that. And I think it's possible to make a check to go, sliding window from left to right as you go through. You can check every single one to see if the remaining is a subsequence in ON. So overall ON log n. So that's kind of how I want to try it. So I'm going to try this after we finish this one. So this one we see has like 70+% passing rate, right? 78. So that's like a fake medium. Might be an easy one. We'll see. So given a string, partition the string into one or more substrings such that the characters in each substring are unique. That is, no letter appears in a single string more than once. Return the minimal number of substrings in such a partition. Now that each character should belong to exactly one. So the first one we can partition into 4 is the minimum number, because if you partition even fewer than that, then you hit a duplicate. Okay, so is this binary search as well? Huh? I don't know. Just guessing. So we want the minimum, right? And we want it to be unique. So I think, maybe we can greedy this, right? Maybe we can greedy this, just starting from the front and just go through, because we want each one to be as large as possible, right? Each substring to be as large as possible. And greedy can definitely do that. So for the first example, we can do AB, right? We cannot do A. So AB, AC, AB, A, right? AB, AC, ABA. That one works. Would it be what is greedy is gonna be the optimal? Let's see. So you're doing greedy. So if there is a possibility that's not greedy, which can get better. So let's say greedy give me 4, and you say if I don't do greedy, then I can do 3. So I can do this and something else, and then we can do 3. So if we can do 3, which means this is all unique, this is unique. Huh. I'm trying to prove that greedy works. Yeah, let me say if there is something else that can result in a smaller one. Suppose we can do a smaller one. If we can do a smaller without using greedy. What do you mean without using greedy? Is if we see there's more we can go, we don't go, right? And then we group them together, right? Then we can always move that to the front. Yeah, so the greedy will always work. greedy will always work. We can always move this to the front. Yeah, we can keep moving to the front. Yeah. Yeah. So no matter what, right? Basically, like if we say this is not greedy result, right? And then we say we have this result, we say this is smaller. But when that happens, we can always turn that into greedy because we can always move this one here, right? Unless you say, unless if we cannot move, then a greedy cannot move either. Yeah, so this is greedy. Oh, greedy is not difficult to code. No wonder it has a very high passing rate, because greedy. Okay. All right, so what we're gonna do? What we're gonna do is we will set up a set. Okay, so scene, that can be a set. Then what do? We just go blah 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 blah. See if it's in the set, if it's in it. Okay, so we say for, and then we say rest equals to 0. Okay, for letter in S if letter not in scene, right? Scene dot add else rest plus equal 1 scene dot clear. Huh. Might as well do this. If letter is in scene, right? If letter is in scene, then we do this, then we do scene dot add. So blah 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 blah. At the end, we say the last one. The last one, if letter is in scene, we'll do this, and do this. If it's not, so return rest plus 1, because we have to handle the last one. I'm pretty confident, so let's just try. Okay? Just try this and see if it works. Okay, this looks to be good. One. Okay, so let's try, let's say A by itself. I think it's the last test case I'm gonna try. Yeah, I think it's right. Yep, it is correct. 2005. Hey, 995 days to go before I can post another post. Damn. 2405. Greedy. Try to group the max a substring, a substring with unique letters. Try to find the max substring with unique letters for each partition going from left to right. Okay. Shall be the result. Greedy, yeah. What? What is that? Last seen is larger equal to substring star. Oh. Bit manipulation. Huh. Yeah, you can do bit manipulation. Yeah, this is not tough for sure. Okay, so that's that. Let's go back to this one. Okay, so yeah, this is not working. I'm not trying this anymore. So we're gonna try binary search. Okay. All right. So let me go through my idea one more time. So when we get the length, right, we're gonna take this whole length out, and what we can do is to try to find if the remaining, right, if the remaining is a subsequence, and to find the subsequence, we can write a separate function to find if it's a subsequence, right? But we don't want to write a separate function because we need to not only get, actually maybe easier from right to left. So we have the left bunch, right? And then we go from the first one. And then we're basically gonna go from left to right, try to find out if we can, like the best way we can fit a subsequence with that. Okay, the best way we can fit a subsequence. And when we do that, we want to put everything as left as possible. Right? We want to put everything as left as possible. As left as possible. Which means we're just gonna go from here. 2 pointers, right? And then we go, we match, move, match. Once we're done, then we have that, right? And then I will go from this position, just go move 1, right? Move 1. So we move 1, we will pop, okay? We pop 1, and we want to find the max. We want to fit this, right? And then we want to fit this, fit until we cannot fit anymore. I mean, if you talk about it that way, I might as well just go through the whole thing at the beginning, right? Then we have the entire thing, and then we can just get there. We get there, right? And then we get there, and then we go 1, 1, 1, 1, 1, 1, and 1. Yeah, we can try as much as we can. Okay? Which means if we go left to right, go as much as we can, and we stop at a certain point. Okay, so that will be the maximum match from the start. Right? The maximum match from the start. Let me think. The maximum match from the start. So he's telling me that we don't have to consider the rest? Yes, because if we have something that doesn't match, right? If I have something that does not match, if we have something that does not match, that means this one must be removed, which means we need to start from Hey, hold on. Initially we say we'll remove this, and if this doesn't work, then these would definitely not work, right? So when you start, get half is here, and then we need to move, right? We need to move, so which basically just means it's not happening. So it has to start from here. And then move to the left, right? We move to the left. Interesting. Maybe. I don't know. I'll give it a shot. Hold on. I actually have let me think. So we go left to right and then right to left. So we go two things. Left to right, we have all the positions that it can match. Right? And then we get these indices down. And then right to left, we get all the indices down. Then, every time when we start, right? Every time when we start, it has to start at least at this position, because we have to remove this, right? If we have right to left, we have something that's bothering us, right? And then we have to start from here. And then we move past this, then it will not work. Right? It will not work. Yeah. Then what we can do is start from here, right? And I say, oops, doesn't work. Move until one point where they work. Maybe. Hold on. So left to right. This is actually interesting. I'm not sure, but so we'll do T. Okay, left to right and the right to left. How is it? Left to right to left. We start with all this, right? And then you can say I equals j equals 0. While I smaller than m and j smaller than n, okay? If si is equal to tj, then left to right j equals I. This is where we match. And then I plus equal 1, j plus equal 1. Else, if they don't match, then I plus equal 1. Then it should be minus 1. This should be minus 1. Then we do exactly the same thing. We're going from right to left. So this one will be I equals j equals n minus 1. And then while I is larger equal to 0, j is larger equal to 0. If they equal, then right to left j will equal to I, and then minus equal 1, minus equal 1. Okay, these are just the matching, like where the front of T can match the total match of subsequence of the front of S, and then where the front of back of T match the back of S, like the best type of matching that we can do. Then when we handle that, right, then we can do binary search. We can say low high equal to 0 and what the maximum length is going to be n, let's do n minus n plus 1, so we kind of extend it towards both, towards the outside, okay? And then we say, well, low smaller than high, mid equals low plus high divided by 2, okay? So this is the length we need to try. So we just try, okay, so from front to back, right? How do we do from front to back? We basically say we have the mid, right? So the mid, this length, from 0 to mid minus 1, right? So from mid, we can say a k from mid, right? And what we're trying to say is we remove all this. So we shall just check if this is, we can say if P and Q, okay? So P and Q, P will start with minus 1. Q will start with mid. All right, that's the starting point. We say if P is smaller than 0 or left to right P is larger or equal to 0, right? That's that. And Q is smaller than n. No, Q is equal to n. Let's go to the end. Or right to left Q is larger or equal to 0, right? So this means we have a match, right? If this means, then we have found that mid works, right? Mid works. So if mid works, then we want to go down. So we say high equals mid, okay? Else, oh, what are you doing, man? You have to move. Where's the moving part? God. While Q is smaller than equal to n. Right? Well, Q is smaller or equal to n. Then we say if this, then we break. Right? So we should just break, okay? And then we can say else, which means we go through the entire thing, okay? So everything, if it doesn't go, then P plus equal 1, Q plus equal 1, right? They both, it's just a sliding window. Right, now we break out, or we finish. If we finish, that means none of them fit, which means the current mid is too small, right? We need to remove more. Then we say low equals mid plus 1, continue, right? If we break out, that means it fits. Then we say high equals mid, right? And then blah, 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 we will end when it come out. It's either low plus O, so it's plus equal 1, right? So it means current doesn't work. So I have to plus equal 1, or high equals this. So when we get out, I think low is the smallest one. So we can just return low. Oh, do we dare? Do we dare? This one's pass. Let's try all these. That did not work. Do not work. Oh man, I thought they work, man. I thought they work. I thought they work. Man, this does not work. I don't want to give up right now because I want to try to see how this one. How wrong am I? L2R and R2L. What do we have? L2R BBA 0, 1, 2, 3. The result is 1. Jeez. You serious? Right to left. 6, 4, and 1. AVA, right? AVA. So we start with let's print P and Q, right? This is where we start. Let's print M and print Q, PQ, okay. Print PQ, and then here we're gonna print mid, low, high, mid, okay. Low, high, mid. So we have say length is 4. So length is 4. So we say 1, 2, 3, 4, right? So Q is equal to 4. Yeah. And then R2, 4. 0, 1, 2, 3, 4. So it works, right? So we break out. And then high equal to mid. So high equal to 4. So next time is 0, 4, 2. And 0, 4, 2. And we start 2, right? So 0, 1, 2. 0, 1, 2. So it doesn't work. So plus 1, plus 1. So now we have 0, 3. Okay. So we have 0, 1, 2, 3. 0. So this 0, that's 0, 0, 1, 2, 3. Huh? Oh yeah, because 2. Okay, so it's here. So 0 works. 0, 1, 2, 3 doesn't work. 0, 1, 2, 3 doesn't work. Right, so next one we say 1 and 4. 1 and 0, 1. 2, 3, 4. Because this is 3. This is 1, so that does not work. Oh, I see. So if this and this, holy crap. And this has to be larger than this. Dark. How are we gonna handle this if condition? Okay, this is an interesting if condition. Maybe we can do the reverse. Maybe the reverse is easier. So when does it fail? Well, it fails if it's negative. If this is negative, or this negative, or Yeah, there's still gonna be a lot of things to go through. So fail is one of them is negative, right? Or, yeah, so we can just say if p is larger equal to 0 and L2RP is smaller than 0, or Q is smaller than N and R2 LQ is smaller than 0, or P larger than 0 and Q smaller than N and L2RP is larger than R2LQ. What do you think? I think this covers them all. So this is failed situation, right? So in this time we fail, then we can say else or break. Then we pass this one. See that? Then we pass this one. Okay, let's try them again. We don't need this. Oh my god, the first one doesn't pass. How about the other two? Other two pass. Okay, let's see what happens with the first one. Okay, first one. Result is 2. Interesting. Low is already to 1. And low equals mid plus 1. Break is one we find, right? This is the one we don't find. Hold on. So 0, 5, 2. So remove 2. And we actually find that it works, right? Remove 2, it works. Therefore, we say 0 to 2. Now we're going to remove 1, right? So remove 1. So we want to see right to left on this. No. Remove 1 is remove here. Remove this one, right? So we have a Z. That's no good. So now we move 0 and 2. 0, 2. So 0 is good. 2 is good. So that should be good. 0, 2. Why is 0, 2 bad? P is 0. Q is 2. P is 0, larger than 0. And that's a false because left to right P is 1. Okay, that's a false. How about Q is smaller than N? Q is 2 is smaller than N. And this 0, 1, 2, right? 0, 1, 2. Hold a second, that's not right. How come? Oh, Lord. I did this one wrong. I shall be n minus 1. There we go. There we go. All right. Oh, look at this. Look at this. This might actually work. Holy crap. This might actually work. All right, let me remove all the things here. I Yeah, that's all the test cases. Yeah, well, that's all the test cases. I copy and paste all the test cases from yesterday. Do we dare? Yeah, let's try it. Okay, it doesn't work. It does not work. Alright, let's see. What the hell? What the hell? Answer is 1. Okay. So we remove 1. B, B, E. We have B, B, E, C, D. Yeah, we either remove B or remove D. Okay, let's take a look again. I bet it is something I did not do well. Hold on. This one works. Okay, looks pretty good. Where did we go? We go to, look at this. We go to 0, 1, 0. We go to 0, 1, 0. Wait, how can we go to 0, 1, 0? How is this 1 is fail? We need to see this. We need to see this. Okay. Okay. We have a 0, 2, 1, and then we go all the way to 3, 5. 0, 1, 2, 3, 4, 5. I say I remove this. Why'd you go there? You should keep moving forward. Right? You're not supposed to get out. Oh, I say it works. Oh yeah, this one means it works. Right? This works. This works. So I want to get even lower. Right? And when I get even lower and 0, 1, 2, 3, 4, 5. 4, 5. Huh? Wait. Hold on. They cannot. Maybe I should change this to 1. So we have to set the lower bound. Okay. We set the lower bound so it won't go down to 0. Like, that's kind of complicated thing. Yeah, I don't think it will hurt the other ones. No. It hurts this one. Oh my god. All right. It's just I think the method is right. It's just a binary search. Oh my god, I hate this. Let's consider one more time. So what was wrong with this equal to 0? I mean, honestly, I probably should do -1, right? I shouldn't even do 0. Yeah, it's okay. So here's 0, so we hit this, right? And then we'll start -1, 0. Because we want to see if it works, right? If it works. So what happens if we have this -1 and 0? Then we'll check, right? We'll check the 0 now. This is now good, and this is now good. And at a certain point, I go all the way to 4 and 5. So P is 4, Q is 5. 0, 1, 2, 3, 4, and 5, right? That's P and Q. And P is larger than 0, 1, 2, 3, 4. Oh, equal to. Damn. Equal to. That's the problem. All right. All right. I think this one's right. This is larger than equal to. Yeah. Okay. Come on. Come on. Come on, y'all. Oh, yes. Oh, yes. Oh, yes. Oh, wow. Oh, terrible runtime, but oh my god. Oh my god. Yeah, this is a tough one. and it's bad. And the runtime and the performance is actually quite bad. Alright, we need to check the solution, but before we do so, we will we'll make something here. So this is binary search. Oof, binary search. Produce two arrays, L to R and R to L, which records L to R records the earliest, the leftmost match from S to T, right? At each index of T. The leftmost matching index of S to T at each index of T. R to L records the rightmost matching index of S to T at each index of T, going from right to left. So I have to make this one as well, going from left to right, right? And we binary search. The important observation is that the score is equal to the length, right, of the leftmost and rightmost letter. It's equal to the length of the substring, right? The substring bounded by the leftmost and rightmost removed letter. Since after the removal, the remaining T is a subsequence of S. Thus, if we remove the entire substring bounded by the left and rightmost removed letter, the remaining shall also be a subsequence of S. Therefore, we just need to find the smallest substring in T to remove, such that the remaining is a subsequence of S. Now we can use binary search to find the smallest substring length. For each substring length, right, we can do a sliding window. okay, from left to right, and check, right, and check whether the removal of the window at each position results in a subsequence of S. Now here is where L to R and R to L comes into play, right? We just need to check, right, the left and the right bounds of the removed window, right? Check whether the left and right bounds remove window oh, it's hard to explain, right? We just need to check. Oh, hold on, let's do this. Suppose the removed window is from index P to Q, right? We just need to check whether R to R, P, right, is larger than 0. Right to left, Q is larger than 0. And left to right, P is smaller than right to left, Q. If all three is satisfied, then we have found a subsequence, and we can shrink the size down. Otherwise, if the entire sliding window does not produce a subsequence, we have to get the size up. Yeah, there are more nuances, right? There are more nuances in the actual sliding window. E.g., P shall start at -1, and Q can end outside T. But that is the gist. So the runtime, we have OM plus ON, OM plus N, just at the beginning, and then plus N log no, this is M. This we go M because we only go M, so this is actually M log N. A pretty bad runtime, but that's okay. We solved it. Oh, what a journey. All right, I guess that's it. We will do definitely check discussion tomorrow. But yeah, we'll leave it as, oh my god, it was good, right? It was good. It took a while, but we got